Hi there, welcome to your lesson on the second law of motion. This is just a recap of what we did in class together. So if you were absent perhaps, or if you just want to kind of see it again because your notes weren't great, then take a look and here we go. Second law of motion. Began first of all by just asking you, what do you already know about Newton's second law of motion? And we definitely had a variety of answers from the class yesterday, anywhere from nothing, I don't remember anything at all, to just some random things, maybe about force and mass and acceleration. So we kind of took it from there and then said, well, let's talk about what the second law of motion is about. We gave some examples here and I really asked in the class, these questions: who's winning this race? And so you have here a group of eight guys pulling or rowing a boat versus one person rowing a boat. And there's some major differences in these pictures. Obviously, here you have one person. So, in a sense, you're going to have probably less force working on this boat here. This boat probably is going to have more force because of the number of people involved. At the same time, you also have less mass in this boat, where this one has more mass. And that difference is going to impact perhaps the other element of our second law of motion, the acceleration of the boat. Which one might accelerate faster than the other one? And that's what we have to kind of like start talking about and figuring out, okay, how does this actually work? So there's different things. One could win for one reason, one could win for another. This boat might, for example, win a race because it has more force. This one might win a race because it has less mass. But we could also talk about acceleration, say, probably this one's going to maybe get up to speed a little faster, accelerate because of less mass. And this one may have a harder time accelerating because it has more mass. So those things do play a part in how we determine the effect of forces, type of masses on acceleration and the force on acceleration. Another example you might see in the real world is that you come up to a stoplight and maybe your mom or dad is driving the car and they decide, do I want to get behind the big rig truck or get behind just the vehicle? Well, if we're wondering which one's going to go fastest when the light turns green, you probably had that experience where you realize, okay, this little car is going to get going a lot faster. Again, it has less mass. And so because it has less mass, it tends to accelerate a little bit faster than the other car, where this one has a greater mass, so more mass. And so because it has more mass, it takes more time for the big truck to accelerate. So if you're in a hurry, you tend to get behind a regular car, not behind the big truck. But on the flip side, if you want to talk about how fast to get going, if these two things were to perhaps collide into a wall of some sort, the more mass on here is going to create a bigger force if it hits a wall or hits a tree or something like that compared to this. Obviously, you don't want to hit anything if you're driving a car, but this has a greater mass, so it's going to have a greater overall force once it starts going. Another example we looked at was some balls rolled down a ramp. We had a bowling ball here, and bowling balls here usually have more mass than a tennis ball, right? This has less mass. And so if we talk about, well, which one's going to go down the ramp in terms of speed or timing, there's different things you might say. Because maybe it has more mass, it might start moving faster, or it might seem like it's going to go farther or have more force. It's hard to say. This one definitely, because if it's less mass, might have a faster acceleration. This one's going to have more force with it. So they're going to do different things because of the differences in those masses. So it'd be fun to play with those things. But for now, Newton's second law of motion states that the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the mass of an object. So we're talking about the connection between acceleration, net force, and the mass of an object. In one sense, we could say that if the force of an object increases, then we would say that the acceleration of an object also increases. So the more force means a faster acceleration. In a different way, we would say if you increase the mass, then actually the acceleration decreases. This is a direct relationship, and this is an indirect relationship when we're dealing with Newton's second law of motion. Okay. One thing to keep in mind, though, is that this is talking about a net force. And a lot of times when you write about net force, you write it using the Greek symbol sigma and net force here. Net force is the sum of the forces. Recall that at one point you were talking about finding a net force of maybe an object pulled this way with 5 newtons of force and an object pulled this way with 2 newtons of force. The net force in the situation is going to be found by doing 5 newtons minus 2 newtons. And since 5 newtons to the right minus 2 newtons to the left is going to give me with a total of 3 newtons to the right. This is our net force, our sigma force there. And that's what we're talking about. We're talking about forces. This is a force. This could be a force of pull, and this could be a force of friction, right? It could be that as well. But those are small individual forces. We're talking Newton's law. We're talking about the net force. So that is going to be the sum of all the forces going in a certain direction. So keep that in mind when you're using get different values to find solutions to equations here. Newton's second law, as a formula, is often referred to as F equals m times a, or net force equals the mass times acceleration. The other ways this can be written, it can also be written as the acceleration equals the force divided by the mass, and also be as the mass equals the force divided by the acceleration. So those are all things that are different ways you can use that formula to solve for different unknown parts of an equation using the different variables. But do remember, we're talking about the net force. Okay, all the time, think net force. Don't forget that. Okay, let's do some practice ones together that we did in class. Oh, one more thing. Additionally, weight. We talked about weight a little bit in this class, in this lesson. They'll often refer to weight as your FG, which we've seen before. Kind of, we've always think about it as a force of gravity. And it is a combination of the mass of an object and the gravitational field of the Earth. And so the weight of a person is found by taking their mass and multiplying it by the force of gravity. I think with Dr. Getman, you did GFS, right? And that GFS is really going to be that 9.8 meters per second squared. Okay, so the force of gravity. So if I want to find the weight, that's the FG of an object, which is its mass times gravity. Okay, so now let's take a look here. We have a boy and a girl, each pulling an object. The girl is pulling to the left with a force of 4.7 newtons. So here's our object. The girl is pulling to the left with a force of 4.7 newtons. And I can call this my force of the girl, which means the boy is pulling to the right. I'll put here the force of the boy. The object has a mass of 0.5 kilograms and is accelerating to the right at a rate of 3.2 meters per second squared. What is the force of the boy on the object? So what we don't know is the force of the boy. So to resolve a problem like this, there's actually a couple steps I need to do. We're trying to find out this one component of this force diagram, a free body diagram, the force of the boy. I know what the girl force is, but I want to find out the boy. So what'll help me do this is, the first step is I want to find the net force of the entire free body diagram. Well, the net force is going to be equal to the mass of the object times acceleration. So our net force in this case is going to be equal to 0.5 times acceleration of 3.2. So my net force on this free body diagram is going to be equal to, uh, sorry, I'm just getting my notes here. What did I write down? There we go. It's going to be equal to 1.6 newtons. So that is the net force on the whole situation here. Okay. And because it's positive, it probably would also probably indicate it's going to the right. Now we want to find the force of the boy. Well, the force of the boy is part of the overall net force. And we find that generally from prior lessons, the net force is found by doing the force on the right of the diagram, or on the upper part, the positive force, is the force of the boy minus the force of the girl. That's the sum of the forces acting in this situation here. Well, I now have a net force. I also have the force of the girl, so I need to find that one. So now when we plug in our variables, I have a 1.6 newtons of net force equals the force of the boy minus the force of the girl, 4.7 newtons. So now I'm going to add 4.7 to both sides. So that 6.3 newtons is the force of the boy. All right. So really we have a couple steps here that are helpful. I find that if I begin with drawing the free body diagram, it helps me know what's going on in terms of what's the picture. I put down my known entities here. What are the things that I know? I knew the mass, acceleration, and I also write down what am I trying to find out. And then I found my net force using this equation, and then use that value to then figure out the remaining missing part for the force of the boy. Let's try that same process now for a different problem. It says a water skier, an 80-kilogram water skier, is being pulled by a boat with a force of 220 newtons, causing the skier to accelerate at a rate of 1.8 meters per second squared. What is the force of the drag? So as a free body diagram, here is our water skier who has a mass of 80 kilograms pulled by a boat. Let's pull him this way with a force of 220 newtons. Now, if you're water ski before, you know that you're not holding onto the boat. You're being pulled by holding onto a rope. So we would call it the force of tension. We want to find out what is the opposite force happening on the skier. And it says force of the drag here. So that's kind of that friction force that's dragging behind the boat as the water ski is going. What is that value going to be? We know the acceleration rate is 1.8 meters per second squared. So once again, we have our free body diagram. We have our known entities here. I should also make note of what am I trying to find out? My force of friction. So as we solve this out here, begin once again to start with, let's find the net force. Net force is found by doing sigma F for net force equals the mass of the object, which in this case is the skier, times the acceleration of the object. So our net force is going to be equal to 80 kilograms times 1.8 meters per second, meaning that our net force is going to have a value in this case of 144 newtons, right? So that's again saying that the sum of these two values is going to be equal to 144 newtons. And again, it's positive, it's going to be moving to the right, right? And that makes sense because the boat is pulling the skier out of the water. So now let's find our force of the friction or the drag. The force of friction or drag is found by finding or using the net force, which is equal to our Ft minus our Ff. And I have some values to plug in. I have 144 newtons of net force equals my force of tension, 220 right here, minus the force of friction, which I don't know. So now I simply need to solve for the F part. So I want to make this positive, so I'm going to add F to both sides. So my equation now is F of F plus 144 equals 220. Now I'll subtract 144 from both sides to find that F of F is equal to 76 newtons. So the value here is 76 newtons of force, which makes sense because 220 minus 76 is 144. So that is the force of drag on the skier being pulled by the boat. So the force of 220 newtons, who weighs 80 kilograms, accelerating at 1.8 meters per second squared. So that's horizontal directions. Let's take a look at a vertical example. We have an elevator is moving up at a constant velocity of 2.5 meters per second squared. There's a person in the elevator has a mass of 85 kilograms. What's the force of the floor on the person? So the free body diagram, we would have the person here in the elevator, and we know that the person is standing on the ground, which means they're pushing down with a force of gravity, an Fg. And we also know the force of the floor is pushing back up at them with that normal force, force in. So the force of the floor is the force in, and that's what they're asking us to find. We know we have a mass equal to 85. But what's interesting about this problem is it says that there's a constant velocity. Because it's a constant velocity, it's not accelerating, then we actually don't have an A value. We don't have an A we can use to use our net force. It's not going to work that way. So I had to think this one through a little bit. So in this case, because I have a constant velocity, that means I'm in a state of dynamic equilibrium, which means that my normal force is equal to my Fg, gravity force, and that's going to be zero. And the whole thing is really going to be balanced. So knowing that, if I can find one of these values, I can know what the normal force is. And I do have a way of figuring out the Fg of an object if it's not experiencing acceleration. That is the weight of an object. So the weight of an object is the Fg. And that is to be found by taking its mass and multiplying it by the weight of gravity, your GFS. So in our case here, we're going to say the 85-pound person times 9.8 gives me 833 newtons for our Fg. And because we said Fg equals Fn, then the force on the floor, or the normal force, is also 833 newtons when it has this constant velocity there. So let's keep this number. We're going to use this number in the next problem. The force of gravity on the person is still 833 newtons. But now it says the elevator accelerates upward at 2 meters per second. So we're accelerating at 2 meters per second squared. How much force does the floor of the elevator exert on the person now? Well, their mass hasn't changed. That's still 85. And in terms of our free body diagram, here's our force normal. Here's our Fg. And now we still want to know what is the normal force on the floor. Well, at this point now, we're back to saying I have an acceleration, and I have some masses, I have an Fg value. So I can go back now and say, well, now we can find, first of all, the net force on this object. I know the Fg is 833 newtons. This is the part that I don't know. So to find that, we'll find the net force, and we'll say that's equal to the mass of the object times the rate of acceleration. And in this case, the mass is still 85 kilograms. And the acceleration in this case is 2 meters per second. So in this situation here, I have 85 times 2. So the net force is equal to 1,000 and, oops, yeah, that's right. It's equal to, sorry, wrong number, is equal to 170 newtons of force. That is going to be my net force in this situation here. So now we'll use that information to say, well, our basic equation to find net force is finding the sum of the components. And so the net force is equal to, in this case, our positive one, Fn, our normal force, minus our Fg. So our net force of 170 equals the normal force, which we don't know yet, minus 833. So to solve for the normal force, we'll add 833 to both sides. And we'll have 1,003 newtons is the normal force, or the force of the floor on the elevator as it is accelerating upwards, which makes sense to have a greater value here than here because I'm moving in this direction. I'm moving up 170 newtons of force moving up, which is why I feel that acceleration. Now, the elevator hits the top floor, and then when it gets to the top floor, top of the building, the elevator begins to accelerate downward at a rate of 3.0 meters per second. Now, how's the floor doing? Well, our Fg remains the same at 833. The mass of the object is still the same at 85 kilograms. Our new acceleration, though, is going to be negative 3 meters per second squared. And it's negative because it is going down. It's accelerating downwards. We're not going to ever have a negative mass. You can't have a negative value for a weight of something, but we can have a negative acceleration to demonstrate that it's moving in a different direction. So our Fn is here. We don't know what that is still. Our FG is here with 833. And now let's see if we can figure out the force of the floor. Once again, let's start with our sigma F, our net force, is equal to the mass of the object times the acceleration. So we're going to say 85 times a negative 3 equals our sigma F. And 85 times a negative 3 is going to be equal to our sigma F is equal to negative 255. So we go then to our next equation, and we say that the net force is equal to F of n minus F of g. So we have a negative 255 is equal to our normal force, which we don't know, minus our negative 833. So to solve for F of n, I'm going to add 833 to both sides. So I have 833 minus 255. And that's going to give me a sum of 578 newtons of force for our normal force on the floor. Okay. One thing I want you to notice as we kind of move forward here is that both of these equations use sigma f in order to find the other part, which means that I can actually say that the mass of an object times its acceleration is equal to the normal force minus the force of gravity. And I could set that as a true equation. And if you were to do the same problem using those values, you'd actually come up with the same solution of 578 newtons because you're just doing them all together instead of doing in two separate parts. So now the cable suddenly breaks in the elevator. What's the force of the floor now? Oh my goodness. Well, the force of gravity is still going to be 833. The mass is still going to be 85. But now I have the cable break, which means I'm going down. I'm going to be accelerating, but I'm going to be going at negative 9.8 meters per second because I'm now dropping. I am going down. This is not good news for me. Okay. And I want to know the normal force in this situation. So I know that the net force of an object is the mass times the acceleration. And so the mass is still 85 and we're accelerating downward at negative 9.8 meters per second. So we're actually going down at negative 833 newtons of force. That's our force there. Then we go back to our initial equation. Sigma force equals the force of normal minus the force of gravity. And we would say, all right, let's plug these in. Negative 833 equals our normal force minus our FG, 833. So when I add 833 to both sides, I get 0 equals the force, normal force on the floor. So not a great day for the person in the elevator, is it now? Okay, so if we complicate things a little bit more, um, we have back to our boxes and our angles. So let's say a box has a mass of 25 kilograms. To find the weight, we said the weight was the Fg equals the mass times that gravity, right? So our weight of an object in this case would be 25 times 9.8, meaning that in this situation here, our object is going to have a weight of 245 newtons of force. That's our FG in this case here. So let's keep this number in mind as we move on to the next step, right? That's the first thing. I have an FG value. Now I take that box, which has an FG value, we said, of 245 newtons, and it's sliding down a ramp at a 40-degree angle with no friction. And ask me two questions. What's the acceleration and what's the normal force? So let's go back to our drawing that we've done a few times now and see what it's asking us. Here's our box. And it gave us some information, said that the angle here is 40 degrees. We know there's no friction. And we do our first step. We said draw your dot on a box and draw your normal force, Fn. and then draw your arrow down here for your FG value. And then what we've been doing is breaking this into its component parts. We take a line that lines up with the Fn, and we draw this vector here, which becomes our FGY. And then we take a vector here to connect it to make our FGX. And we make a right angle triangle. This angle right here, because the way we do this, is going to be equal to that angle. So this is 40 degrees. So if I was to redraw this separate from the diagram, I have this line for FGY. I have this line for FGX. And I have this hypotenuse for my FG. Here's my angle there at 40 degrees. So this triangle is the same as what's right there. Now, knowing this information, we can start to solve some problems. Okay, here's what I know. What I know is I have an FG. This value is 245. I know that across from the angle here is my opposite side, and the one next to it is my adjacent side. So that's my triangle setup to work with my trigonometry ratios. Okay, so that's my FGY, my FG, and my FGX. So that's what what I have to work with so far. You good with this? Now I can remember back to my information about sine and cosine, that the sine of an angle equals the opposite over the hypotenuse, and the cosine of an angle equals the adjacent over the hypotenuse. So the question is going to be, which value do I want for which element? I want to find acceleration, and I want to find the normal force. Let's get out a different color here. Let's look at, first of all, acceleration. Acceleration is going to happen, so there's no friction. Our force of friction is this part here. So that's what's holding it on, and there's nothing here. So we're accelerating, which means we're going down the ramp this way. Well, the line that runs parallel to going down to this friction force is going to be the FGX. These two lines are connected because that's going to talk about the acceleration of the object as it goes down the ramp. So because there's no friction here, and that's a zero value, my FGX becomes my acceleration rate. So the FGX is actually my acceleration value is going to be found by finding the FGX, or my opposite. So for acceleration, I want to use the sine equation here. All right, so let's draw a little line. Let's draw a little line here. And this is going to be for acceleration. So acceleration is going to be the sine of an angle, which I know is 40, is equal to the opposite, which I don't know. That's my FGX, divided by the hypotenuse, which is 245. So I'm going to do 245 Newton times the sine of 40 to get my acceleration amount. And when I do 245 times the sine of 40, I come up with 157.48, or if you round that to the nearest tenth, 157.5 meters per second squared. So that's my acceleration, because this value here is 157.5 on there, which makes that awesome 157. So that's my acceleration, 157.5 meters per second squared. Let's do the same thing with normal force. The normal force is going to say, well, if it's not flying off the table, this value is equal to this value. So my FGFN is actually equal to my FGY. So this is going to be my FGY is also the same as my FN. They're equal to each other. So that's my adjacent side. So my normal force is found using cosine theta. Cosine of 40 equals the adjacent, which is FGY, divided by the hypotenuse of 245. So 245 times cosine of 40 gives me my FGY, which is still Fn. And that's going to give me a value of 187.68. If I did the nearest tenth, I would say 187.7 newtons of force is equal to not just FGY, but also my normal force, 187.7 newtons. So the process itself is not super complicated as long as you can take a look at, I think, take this picture here. And if you can extract that triangle and get it separate so you can see what your component parts are, it might help you understand how those things work together a little bit better. Okay, I think that's all I got for today. Yes, it is. Hope that helps you with your assignment. Good luck with all that. Have a great day.